In this lecture, I'm just going to continue with the enzyme kinetics. In the previous lecture, I think lecture 6, I talked about Michaelis-Menten kinetics and how to derive it. I think I, I showed how to derive this expression. So this Michaelis-Menten kinetics or Michaelis-Menten expression, kinetic expression. So I showed this expression. I showed you how to derive this expression based on some theoretical assumptions, and I also showed the chemical reaction. So how Michaelis and Menten originally obtained this expression. Yeah, you have an enzyme substrate complex. From there you get your enzymes plus products. So the rate of reaction depends on this particular parameter, which is concentration of your enzyme substrate complex in the reactor at any time. So just remember. And I also talked, so this mu, whatever it's here, it's called initial velocity. And then I talked about the units. So if you want, you can express in terms of milligrams per liter per minute. Imagine if you show the plot of time versus product concentration expressed in milligrams per liter. So this is your initial velocity mu here. It has an unit of milligrams per liter divided by minutes if time is expressed in terms of minutes. So what this slope, it says change in product concentration with respect to time. So this is nothing but equal to your initial velocity. So whenever you talk about enzymatic reaction, always think about initial velocity, and this is how you are going to get it. Yeah. So product concentration that you can monitor during a biological reaction, and you can monitor how it changes with respect to time, and then you can plot, and then you can get the slope value from this area, and then you can get your initial velocity, or if you want you can call it as a specific rate. So these are no, just call it as a initial velocity because we are talking about enzymatic reactions. So if you want, you can divide this. You say mu is equal to mu max substrate concentration Km plus substrate concentration. In both sides you can divide by the total enzyme concentration. So divide by E total. So you can rewrite like this: mu max by E total substrate Km plus S. So in this case, you can also express mu in terms of imagine your total enzyme concentration is milligrams. So you can express the unit of your initial velocity in terms of milligrams per liter per minute per milligram of catalyst. So this is one way. And in case if you are expressing your total enzyme concentration in terms of milligrams per liter, then your initial velocity, the unit will be milligram of your product per liter divided by milligram of catalyst per liter multiplied by your time scale minutes. So liter get cancelled, so it will be equal to milligram of product per milligram of catalyst. If you check in the books, people would use different type of units. You can find this type of unit, milligram per product divided by milligram of catalyst per unit time, and then you might even find this unit expressed in terms of milligrams per liter per milligram of catalyst multiplied by minutes. Yeah? So you must pay attention to units. So whatever the units that you are seeing here, that depends on how you express your product concentration, what's the unit of your time scale, and what's the unit of your catalyst. So depending on that, the velocity of the unit for your initial velocity will change. So these are some things you should remember. Pay attention, especially when you are going to solve some problems. Yeah? So how to get these parameters. Say mu is equal to mu max multiplied by your substrate concentration, and then Km plus your substrate concentration. So how we calculate this maximum velocity and Km? Yeah, how to calculate this value? So so how do you get it? Yeah, so that number is you have to linearize these expressions. Yeah, so how can we linearize this expression? So you can take inverse on both sides. 1 by mu is equal to Km plus substrate concentration mu max substrate concentration multiplied. So you can expand this part, Km by mu max into substrate concentration plus substrate concentration divided by mu max multiplied by your substrate concentration. Yeah, so this and this get cancelled, so you will eventually end up with some equation like that. Mu max multiplied by your substrate concentration by 1 by mu max. So this is something you must remember. So this one looks like y is equal to mx plus c. So c is your intercept. I hope you all know this equation. If you have y, if you have x, if you have some linear line, slope will be equal to m and intercept will be equal to c. So the line best fit this, the equation that best fit this line will be equal to y is equal to mx plus c. So here your y will be equal to 1 by y, your slope will be equal to Km by mu max, and your intercept will be equal to 1 by mu max. So we can plot if you have mu value and if you have your substrate concentration, then you can plot like this: 1 by substrate concentration, 1 by mu value, because this is your y, this is your x. So you will get something linear line. If you plot your experimental data, you can take the best fit line like that, then you can calculate that slope, and that slope will be equal to Km by mu max, and your intercept will be equal to 1 by mu max. So from your intercept you can calculate your maximum velocity, maximum initial velocity, and from that you can calculate your Km value. I hope you all know how to calculate this one. Yeah, so it's not a difficult one. So imagine if intercept is equal to 1 by mu max, so 1 by mu max will be equal to 1 by intercept, and we all know slope is equal to Km by mu max. So therefore Km will be equal to slope multiplied by your maximum initial velocity. Yeah? So that's how you get your value. So if you have your substrate concentration and if you have your specific growth rate, say some number here, all you need to do is take 1 by substrate and then take 1 by your initial velocity, and then you plot them. What is the value here? So 1 by s, and then 1 by mu, you get some plot. You take the best, you draw a best fit line, and then you take the slope, and then you calculate your intercept. From that you can calculate your Michaelis-Menten constant. So this expression which I showed here, I'm going to write it here: 1 by mu substrate concentration plus 1 by mu max. So we call this as sorry, the plot which you generate using this type of expression, say 1 by mu and 1 by s, and the slope which is equal to 1 by mu max, and that intercept value which is equal to km by mu max. If you want, you can extend this line that cuts across this x-axis here. This value will be equal to minus 1 by km. So this plot which you see here, people, many books they call this as a double reciprocal plot. Double reciprocal plot, or to give the credit to the scientist who first used this type of expression, Lineweaver and Berg plot. So these two guys, they came up with this expression, Lineweaver Berg plot. So you can get, so Lineweaver Berg plot, this is a very good method to calculate or determine the Michaelis-Menten parameters. So which is nothing but your maximum initial velocity and your constant equilibrium constant Km. So these are the things you should remember. So you can use this particular expression, so you can use this expression. I just forgot to mention why we call it as a double reciprocal plot. You see here 1 by mu, this is reciprocal of your initial velocity, and here this is 1 by substrate. So this is a reciprocal of your substrate. So you are plotting these two values, one in y-axis, another in x-axis. So that's why it's called as a double reciprocal plot. So this method so far we discussed is called Lineweaver and Berg plot method. If you want, you can use other type of expressions. For example, you can linearize this expression, which is your Michaelis-Menten expression, into different forms. In three different linearized form. So one is I'm going to write here. I'm not going to derive. I will just show what are those expressions. If you want, you can work in your home. It's very easy to get these expressions. And then another one is minus 1 by Km, your substrate concentration. Another one, mu by your substrate concentration, which is equal to Km multiplied by mu max, Km multiplied by mu. So these are other way to linearize your Michaelis-Menten expression. So this is a non-linear version. If you plot mu versus s, you will get some curve like that. This is a non-linear curve. So it's not anything linear relationship. It's a non-linear relationship between your initial velocity and your substrate concentration. So these are the things you must remember. So if you want, you can use the Lineweaver Berg plot, or you can use, for example, this equation. If you are using this equation, then let me write here. So in this case, your y value will be substrate concentration divided by your initial velocity, and your slope will be equal to 1 by maximum initial velocity. So this will be your slope. So your x will be equal to your substrate concentration, this one, and this will be equal to your intercept. or C. So, so all you need is to plot your substrate concentration here. Y is equal to mx plus C. So you will get something like that. You draw a line, best fit line, and then you take the slope. So you take the slope. That slope will be equal to 1 by mu max, and your intercept will be equal to Km by mu max. So mu max will be equal to 1 by slope. So Km will be equal to intercept multiplied by your maximum initial velocity. Yeah. Hope everybody is following this one. These are not really difficult. These are simple mathematics. All you need to know how to linearize your expression, and that's it. And one more thing you have to remember. I showed you in the previous lectures, mu max is equal to K catalyst multiplied by E total. So if I give you this maximum specific growth, so okay, if I give you this data, say your initial velocity expressed in grams per liter per minute, and substrate concentration say in milligrams per liter, and if I give you the total enzyme concentration, say some x grams, then if I ask you to calculate this catalytic K catalyst, then you can calculate using this simple expression. So first you need to use the Lineweaver-Burk plot, and then you take your slope, you take your intercept. So from that you can calculate your mu max and Km. So from mu max you can divide this by total enzyme concentration. That will give you some number which is called K catalyst. Okay, just imagine I give this enzyme total enzyme concentration in milligrams per liter. I already taught you why you have this unit milligrams per liter. In this previous lecture, you must listen to previous lectures. Only then you will understand the units. As I said, I talked a bit about how they purify enzymes and how they test the purity of the enzymes, and there is no accurate measure to say like what's the mass of enzyme in a liter of solution. I said to you, like, they open the cell and then they try to separate the enzyme from the fermentation broth. So they try to purify few times, and then they try to do some experiments to monitor product versus time concentration, and then they will wait until it reaches the maximum initial velocity. So which means your enzyme is very pure at this stage. So which means each batch you have less amount of enzyme in that per liter of your solution. So try to listen to lecture 6, only then you will understand why your enzyme concentration is milligrams per liter. But I think in few books they also express in terms of milligrams. So probably they must be using some freeze dried products. So always pay attention to the question. So what's the unit of your enzyme concentration? So imagine if your mu max is expressed in grams per liter per minute, and your total enzyme concentration is expressed in grams per, say, milligrams per liter. You can convert it into grams per liter. So K catalyst will be equal to mu max by E total. So what is this? So this will be grams per liter multiplied by minutes. Minute is the time. So you all know the unit of mu max, yeah? So this is grams per liter per minute. So that's why you have the minute here. So liter get cancelled, grams get cancelled. So k cat, it will be equal to some number divided by minute. So I already said to you in the previous lecture, this number per minute is nothing but turnover number. So this number just reflects how many molecules of your products are produced per minute by that catalyst. Yeah? So this is your k cat. And always remember, this k cat is related to mu max, not to mu itself. Imagine you have a plot of your substrate concentration, your mu value here, and you plot it here. Yeah. So this is your maximum initial velocity. So you can, why not to get your mu value, say you can take mu somewhere in here, yeah, where it is not, where your initial velocity is not at maximum, so you can get that one. So mu divided by E total, that should give some number related to your catalytic activity, but this is not real catalytic activity. So this is not a real catalytic activity, because this is not at this point. Change the color. So in this graph, at this point, 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 the velocity is changing. Mu is also a function of your substrate concentration, yeah, because when your substrate concentration increase, your initial velocity is increasing. So whatever the mu value or the initial velocity value which you see at this point, so they just represent, sorry, at this point I showed it in the green. So it's also a function of your substrate concentration. So it's not one, so in fact it's not the real property of your enzyme. But when you come, let me go to the next page, mu versus your, but if you take, this is your mu max. So at this point, this is not a function of your substrate concentration, because your substrate concentration is very high and your initial velocity reached a maximum. So everything is constant. So with increase in substrate concentration here, mu remains a constant, and that is equal to your maximum specific growth rate. So at this condition, this mu max, which is a function equal to k cat multiplied by total enzyme concentration, this is only a or this is the property of catalyst. So this mu max is not influenced by your substrate concentration, but whatever the mu max value that you have, that reflects the actual property of your catalyst to convert your substrate into product or per unit time. Yeah, so that's the amount of products formed per unit time. So that's why, so if I give you, say, like if I give you mu value is equal to some number, say milligrams per liter per minute, and I give you total enzyme concentration, say some number per grams per liter, and if I ask you to calculate k catalyst, you should able to say that the data is not enough. Yeah, so which means you must need this value, maximum initial velocity. So try to keep that in your mind. So you need this value mu max to calculate k cat. So this k cat, you can call it as a rate constant, or you can call it as a turnover number. and this Km value, it has a unit of your substrate concentration. So if your substrate concentration expressed in grams per liter, Km will be expressed in grams per liter. I think I forgot to cover the limiting conditions of Michaelis-Menten kinetics. I think I can do that now. So just to remember, so that's the way to calculate your catalytic turnover number and Km value. I hope you all remember the assumptions of Michaelis and Menten. Km is related to your equilibrium constant. So what this one measures, this Km measures how much of your enzyme and substrate they combine to form, or they bind to each other to form enzyme substrate complex. Yeah. So this is something, an equilibrium constant Km. So on whatever, so as I said to you, the rate of reaction depends on the concentration of your enzyme substrate complex. So how much or how many of the enzyme substrate complex are really converted into your product, so that will be dictated by your kcat value. So what we are going to do is like something like you can call, if you want, a chemical reaction, why not? So this is something that kcat and then divided by your Km, which is related to your equilibrium reaction. So this ratio kcat by Km, we call them as a catalytic efficiency. So what it means, so if this number is high, it means almost all the enzyme substrate complex are converted into your product. If this number is low, which means the enzyme substrate complex are yes, so if this number is low, which means the efficiency of your catalyst to convert your enzyme substrate complex into products is less. Yeah, so if I ask you to calculate catalytic efficiency, so that's how you have to do. You have to calculate your mu max. From that you calculate your catalyst, K catalyst, and then from Lineweaver-Burk plot you will also get Km, and then you take the ratio of these two, Kcat by Km, that will give some number which is called as a catalytic efficiency. So I hope I covered this topic. I'm just going to check my notes to make sure everything is fine. I don't want to miss any topic, because this is a really important expression in bioprocess engineering. So I'm going to, forgot to mention the limiting conditions. The limiting conditions of Michaelis-Menten expression. I asked this in the previous year exam. For some reason students, they gave wrong answers half of the class. In fact, it's so simple too. So what you need to do, if you plot your substrate concentration versus your initial velocity, say grams per liter per minute, and then substrate concentration, say grams per liter, and then you get some plot like that. You see here, your initial velocity reached maximum in this part. This red color area. So this is your initial velocity reached your maximum. You can draw a line here. So that will be equal to mu max. Yep. And this line will follow the relationship or expression provided by, this line will follow the relationship provided by Michaelis-Menten. Mu will be equal to Km mu max multiplied by S divided by Km plus substrate concentration. Yeah? So we need to, so one thing we can do, we just take mu max, exactly, if you know mu max, take exactly half, mu max by 2. If you go back to the plot, say if your mu max is here, mu m by 2 will be somewhere around this line. Yeah? So this will be your mu max by 2. Mu max by 2. And then if you draw a line here, this will be equal to Km. So what it states graphically, from this graphical method, what it says is like, when your initial velocity is equal to half of the maximum initial velocity, then the substrate concentration at which your mu is equal to mu max by 2 will be equal to the equilibrium constant Km. So can we prove this mathematically? Yes, we can prove that. Yeah, I'm going to do that one. Just write this equation. Mu is equal to mu max multiplied by substrate concentration Km plus your substrate concentration. So substitute mu is equal to mu max by 2. Say this is equation 1, this is 2. So substitute this value here. So mu max by 2 will be equal to mu max multiplied by your substrate concentration Km plus your substrate concentration. Yeah? So this and this will get cancelled. Km plus your substrate concentration will be equal to twice the substrate concentration. So Km will be equal to minus, it will be equal to, so what it says is like Km will be equal to your substrate concentration when, mu will be, Km will be equal to your substrate concentration at which, yeah, your initial velocity will be exactly equal to half of the maximum initial velocity. So this is one limiting condition, yeah, or one of the Michaelis-Menten expression. And another one, go back to this graph here. If you see this line again, this line, you see here mu max, which is this part. I put a square box. So mu max, that happens when your substrate concentration is very high here. Yeah, which means, and imagine this substrate concentration which you are seeing here, just follow the pen, that's really higher than your Km value. So Km itself is a substrate concentration, refers to your substrate concentration when you are specific, at which your initial velocity will be equal to half of the maximum initial velocity. So we can prove that experimentally. Say for your substrate concentration is much higher than your Km value, then mu is equal to mu max multiplied by substrate concentration Km plus your substrate concentration. So this will be equal to mu max substrate divided by your substrate concentration. So this and this one will get cancelled, so mu will be is equal to mu max. So what does this mean? Like, so when Km is, when your substrate is much greater than Km, S plus Km will be equal to, approximately equal to S. just assume that if your Km value is 0.01 and your substrate concentration is equal to say 20 grams per liter, so S plus Km will be equal to 20 plus 0.01, so this will be equal to roughly 20.01. This is approximately equal to 20 grams per liter. So that's what I stated it using notation. So S plus Km will be approximately equal to your substrate concentration, as K is really higher than your Km value. So this is the second limiting condition of your Michaelis-Menten expression. So that's why you get when you are working at a higher higher substrate concentration, your mu will reach as mu max. And this is true if you go back to the graph. You see here your Km value is somewhere here. I am drawing this area, and then your substrate concentration where you get your mu max, this is really higher than your Km value. So that's the theory of your Michaelis-Menten expression and some of the limiting conditions of this particular kinetic expression. I think with this I think I covered the whole enzyme kinetics, and okay, one more thing I forgot to mention. I already showed you the different way to linearize your Michaelis-Menten expression. If you come back to this page number, this is your non-linear version. This is one way. Say this is equation 1, say this is equation 2, say this is equation 3, this is equation 4. You can also get your Km and mu max value using equation 3, which is here. Yeah? I'm going to write that equation. Or another version, maybe you can call linearized version of MM expression. So mu is equal to mu max minus 1 by Km mu by substrate concentration. So you can plot directly mu versus mu by substrate concentration. You will get some curve like that. So this slope will be negative. So minus will be equal to 1 by Km, and your intercept here, that will be equal to your maximum initial velocity. You have this decreasing slope, so that's why you will have a negative slope, and that will be equal to minus 1 by Km. So Km will be equal to 1 by slope. Sorry, slope will be equal to minus of 1 by Km. Yeah. So Km will be equal to 1 by minus of slope here. So this is another way to calculate your Michaelis-Menten parameters, mu max and Km. So, and this, if you are going to use this particular expression and this type of plot, this expression we call it as I don't know how to spell, Eadie-Hofstee expression. And this plot of mu versus mu by substrate concentration, we call this as Eadie-Hofstee plot. So there are many ways you can get this Michaelis-Menten parameters to get. So if I give you specific like initial velocity at a different substrate concentration, then you should use Lineweaver-Burk plot or Eadie-Hofstee plot to get this two constant. You can use a graph sheet, or you can use Microsoft Excel or any other software which you feel comfortable with, and that allows you to calculate these two parameters. And one more thing, let me check my notes. Okay, yeah, so far we covered this Michaelis-Menten expression, Km plus your substrate. So this type of equation we use if you have a reactor, you have one substrate and one enzyme, yeah, one type of enzyme. Imagine if you have more than one substrate in your reactor. I said to you, sometimes your enzymes can be group specific, yeah. I showed some graph in the previous lectures. Say this is your substrate, this is nothing but ethanol. Your enzyme can recognize this. This is your enzyme. And then imagine you have another substrate, this time COH, H, and then another. So this is another substrate. So this is nothing but methanol. If the enzyme is a group specific enzyme, then it can still recognize this second substrate molecule, and it can act on both of these substrate and then convert them into products. So in that case, you have to use a slightly complex expressions which looks almost similar to Michaelis-Menten expression, and that expression is given by this way. You can write that one like Km. So put S1, your substrate concentration 1, plus mu max, your substrate concentration 2, Km, plus your substrate concentration 2, and then you can put 2. So 2 equilibrium constants, and then 2 substrates. And imagine this mu max is only 1, yeah. So these are different way to, because this mu max is related to your product concentration, change in product concentration with respect to time, and you are using 2 substrate to make only one product, so that's why this value is constant. So I hope I fairly covered this topic. I'm going to stop recording this lecture now. I will upload this one, and then after this I'm going to record a video on enzyme inhibition kinetics. That's very bit more complex than enzyme kinetics, yeah. So I will try to upload one video from YouTube, which you need to see. So in that video will tell you why do we need to study about enzyme inhibition kinetics, yeah. Because most of the drug molecules that we are using to treat, for example, HIV, this drug molecule is nothing but an enzyme inhibitor, yeah? So I will post one link, you must watch it. Probably I might ask some question based on that YouTube video. It's not created by me, but still you have to watch this video. I'm going to stop recording the lecture now, and then I will upload the next one soon. Thank you.